Hi everyone, welcome to the second part of lecture 3. And now that we had a crash course on geodesic convex optimization, we're going to see how to give a gradient descent, a geodesic gradient descent algorithm for the conjugation action problem. Okay, so what is the conjugation action problem? So here in this case, we have the group G, which is the general linear group, acting on the space of matrices via conjugation. Right? And here the null cone is the set of nilpotent matrices. And if you remember the action, we have that an element G will act. So if I have an element A of our vector space V, the action of a group G will take A to G, A, G inverse. Okay, so, all right. And what is the conjugation action scaling problem here? It will be given an input A, which is any matrix, is a nilpotent, right? So, all right. And here, what is our function? So our function that we saw before is going to be the logarithm of the norm of the element like H inverse. And if you think about it, this is essentially H acting on A, right? Which we can write this in terms of the trace. So we have this trace. Oh, sorry, I need a log of the trace. So let me correct myself here. So we have the logarithm. So let's say we have a square here. We have the logarithm of the trace of X, A, X inverse A, right? So here, we do need to have actually a transpose. Okay, and this can be thought of as a function again from the space of positive definite matrices to the reals, as we have seen today, right? So we have this function to optimize, and this will tell us if the matrix A is nilpotent or not. Okay, now again, as we saw before, like the infimum over all these x's when X takes the value as positive definite matrices of our objective function exists if and only if A is not in the null cone, right? All right, so the first question is, okay, we learned about the crash course in geodesic convex optimization, and we need to ask, is this function convex or is this function smooth? And now to decide this, we need to first compute the gradient of our function, right? And how do we compute the gradient? Well, we need to compute the gradient, but we need to compute the second directional derivative. We need to prove actually that the Hessian is, so to prove convexity, we need to show that in any direction in the tangent space, right? So at any point, so the direction H from the tangent space is a Hermitian matrix, we need to show that the second directional derivative is greater or equal to 0, right? Because this is proving that the Hessian, right? So this is equivalent to proving that the Hessian is positive semi-definite, right? But to compute the Hessian, we first need to compute the gradient. So, okay, how do we compute the gradient of our function, right? So, all right, so in this case, we have, all right, our function f, if you remember, fa, let me write it again here, of x is equal to the log of the trace of x, a, X inverse, A dagger, right? Which is the conjugate transpose, right? Okay, so here, if we look at it now at the gradient of FA, right? We know that if we take any direction H by the definition of the gradient, this is going to be equal to the derivative with respect to T of our function, so log of the trace. Now, here, the direction, we're at A and we're going in direction like H, right? So then X in this case becomes ETH. So X here is ETH. Let me just put that X, because we're going the direction H, right? So, and then here we have A, and then I have E minus TH, A dagger. And then we have to do at t equals to 0, right? By our definition of gradient. Now, if we take the derivative, okay, so here now we can just use univariate calculus with some matrix computations. right? So what we have here is we have this derivative with respect to t, but based on the chain rule, what do? The derivative of the log is the inverse, is 1 over the trace, right? So we would have here 1 over the trace of ETH, A E minus TH, a dagger, right? And then we have, let me put a big parenthesis here because we have to take t to 0. Oh, sorry, this is dagger. And then we have times the derivative of the trace function, right? But the derivative of the trace function is what? Well, it's going to be the trace of, well, I'm going to take the derivative of the first element, which is this one. I need to take the derivative of the first element and then take the derivative with respect to the second element, which means that we get, here we're going to have h, a, e to the minus th, sorry, it is h, t to the h, my bad. So it's h, e to the h is the first derivative, and then we have a, e to the minus th, a dagger, and then we have the second derivative, which will be minus e, th, a, then we have times h, e to the minus th, a dagger, right? So now we took the derivative of the trace function, and all of this now we have to evaluate at t equals to 0. So now we took care of the derivative, and once we evaluate it to 0, well, what do we get? First, the denominator, well, ETH, when you have t equals to 0, ETH is just the identity matrix, right? So here we're going to have trace of a dagger, which is what? 1 over the norm of a squared, right? The Frobenius norm. And then we have times, now, again, ETH will be the identity. So here, what do we get? Well, we get trace of, well, this is going to be h, a dagger, minus, and then we know the trace is cyclic, so we can do what? This is going to be a dagger, a h, right? So this is our gradient. But if we want to express this in terms of inner product, right, to really extract the gradient out of it, what we have is this is going to be 1 over norm of a squared times the inner product of a dagger minus a dagger a, just by using cyclic. The trace is cyclic, so this is also h, a dagger a, because h is symmetric. Well, this is the cyclic property of the trace anyways, so it doesn't matter. And we have h, but because h is symmetric, h is equal to h dagger, right? So we can certainly apply this inner product. All right, so then we have here h. Okay, so this is our gradient, which means that in this case, what is the gradient? The gradient is exactly this quantity, normalized, right? So maybe, let me put it in the bottom here. So, or maybe let me put in the next page. So what we found here is that the gradient of f at a is equal to 1 over norm squared of a times exactly the matrix, like a dagger, a dagger minus a dagger a. Okay, and I just want to have this expression because we're going to try to understand what this expression means. What is gradient descent doing later on? Okay, so here we compute the gradient. That's our formula for the gradient. And now, so we're going to discuss what does the optimization here mean when we're doing gradient descent, right? So, okay, so now that we compute the gradient, let's prove geodesic convexity, right? So let's prove that our function is convex. So, okay, and again, so given any direction h, we need to show that the second derivative is greater or equal to 0. Okay, so now how do we compute? So we already computed the gradient. Now let's compute the hashing, right? So how do we compute the hashing? Well, we know that if I take any direction h, we know that h del square f a h should be equal to the second derivative, evaluated at 0, right? So this is squared FA ETH when t is equal to 0. Now, let's compute the second derivative. So let's use the second this like page here to compute the second derivative, or maybe let's compute here and see how far we can go, right? So we know what is the derivative here. So we have to apply two derivatives. So in particular, this is equal to the derivative that we computed before, which is going to be equal to the derivative, and again, which is going to evaluate it equal to 0 in the end, right? So this is the derivative of the first derivative that we had, like 1 over trace of ETH a E minus TH a dagger, right? We had this times the trace of H ETH a E minus TH a dagger minus ETH a H E minus TH a dagger, correct? So let me put a dagger here. So we have to take this derivative, and then after everything, we have to evaluate it equals to 0, right? Okay, so now how do we take this next derivative? Well, this next derivative, we can just use the quotient rule, right? So this is going to be what? So if we use the quotient rule, we're going to have, well, this is going to be the derivative of the first guy of the numerator. And here we can put, what is the derivative of the first guy? So we're going to have a big trace. So let me put everything in the denominator, in the numerator. So it's the trace of, okay, so here I'm going to take another derivative, and I'm going to have H squared ETH a E to the minus TH a dagger. And now I have to take the derivative of the second element of the first guy here, right? And then this is going to be minus H ETH a H E to the minus ETH a dagger, right? So this derivative in blue corresponds to this derivative here. Then we have to do the same for the second term. Then we have minus H ETH a H E to the minus TH a dagger plus, and at last we have the last term, which is E to the TH a H squared E to the minus TH a dagger. And all of this is multiplied by the derivative of the first guy. So let's put it here. Like, so we're multiplying. This expression is getting too big. Let me just see if I can decrease it so that we can multiply properly. Okay, there we go. So we did our computation. Now we multiply this by trace the denominator. So trace of ETH a E to the minus TH a dagger. And then we have minus. So all of this is going to be minus the first term, right? Which is our trace of H ETH a E to the minus TH a dagger minus ETH a H E to the minus TH a dagger. But note now that we have to take the derivative of the denominator. But if you think about it, the derivative of the denominator is exactly this guy in orange. So then all we need to do here is we take a square, and then that's our numerator, and then our denominator becomes trace of ETH a E to the minus TH a dagger. So this is just basic calculus, and then all of this we'll have to evaluate at So if I put it like this, all of this, we have to evaluate at t equals to 0. Now, what happens when we evaluate this huge expression to t equals to 0? So all the e to the th will become identities, right? So in this case, what do we have? Well, let me just use here. Okay, so you can see the expression above. And what are we going to have? So evaluating to equals to 0, we have that this will become, first of all, the denominator becomes just, oh, sorry, there's a square here. So the denominator, we're going to have the norm of a square times square. So we have 1 over the norm of a to the 4th times, now we have the numerator. So what is the numerator? The first term in blue becomes, well, we have a trace. So we have a giant trace, and the trace will be of h squared a dagger, because all the ETHs will become identities. And then we have minus h a dagger. And then we have minus, again, we have h a dagger. So we have minus 2 here. And then we have plus, and then now we have plus, we can just use the cyclic part of the trace, and we have a dagger. Well, we can say just like h squared a dagger a, right? So this is the first one. And then here we have times the norm of a squared, which is just this trace when it goes to the identity. And then we have minus the square of the other guy. So what is the square of the other guy? Let me just put a bigger parenthesis here. Minus what is the square here? This is going to be exactly the trace of h a dagger minus h a dagger a squared. Correct? Now let's just write this in terms of inner products, right? So if we write this in terms of inner products, what do we have? We have this is 1 over the norm of a to the 4th times, and then here we have just the norm of a squared times. Now, what is this first trace, right? Like this first trace in blue. So let me just color code everything. This first trace in blue, right, is exactly the norm of, we have HA. Okay, so the blue part is HA minus AH squared, right? And then the second one is just, if we do in terms of inner product, the second one will be minus, and then here we have the inner product between H and A dagger minus A dagger A squared, right? So this is exactly what our Hessian becomes, okay? And you can see this because let's just prove the blue here, right? So in the blue, what we can see is we can just split. The first term is going to be H A times, well, the trace, right? Like that trace is the same as this trace of HA times A dagger H, right? And this is minus, well, you have 2, and then here we have HA, and then we have HA dagger, right? And then here we have, here we'll have plus, and then we have HA dagger times AH, right? Now, if you think about this, what is this saying? Well, this first guy, right? I can replace this H dagger A as HA, the whole thing dagger, right? So, and then, let me think here. So I have H, so we have A dagger H. Or did I get something wrong here? No, this is fine. Yeah, so we have a dagger H. And now, what is the expression for the square? If we just compare to the expression of the square, we get exactly like, we have HA, the inner product HA minus AH with itself, right? HA minus AH. What is this inner product, right? It's the trace of HA minus AH times, well, we have, now we have to do A transpose, conjugate transpose H minus H A conjugate transpose, right? So if we see what this inner product is, we're gonna get exactly HA times A transpose H, so we get the first term, so this is HA times A transpose H, and then we have minus HA dagger minus AH A dagger H, and then we have plus, and then we have exactly AH, and then we have HA dagger, which was the thing that we just discussed here, right? And then, so the first two terms are good, right? The first and the last term, and now we have to see the second term. But the second term, by the cyclicity of the trace, we have minus 2 HA dagger, right? So this proves that the blue part is correct. So I'm just going to erase it. Okay, let me just delete this. And then the other one, you can clearly see that this is just the inner product and we're squaring, right? And now, how do we prove G convexity? To prove G convexity, we want to show, so we want to show that, let me call this like star, that the star is greater or equal to 0, right? In positive semi-definite terms. But this is exactly what we need. This follows from Cauchy-Schwarz, right? So this follows from Cauchy-Schwarz. And this is the Cauchy-Schwarz version for matrices, okay? So this is for matrices. And what is the Cauchy-Schwarz for matrices, right? Like CS for matrices is just, we have that the inner product of two matrices, let's say B and C, okay, squared is less than or equal than the norm of like B squared times C, norm of C squared. This is the usual Cauchy-Schwarz, but in matrices, in the matrix norm, this is exactly equal to the trace of, you know, B transpose times trace of C transpose. Right, so you conjugate that, like transpose. So, but now if you notice, we just wrote exactly that in terms of our norms, right? So here, what do we have, right? So now what we can do here is, oh, sorry, this is my bad. So here, actually, instead of splitting it this way, right? So what I actually want to do is that the orange is going to be A, take A, and then we have AH minus HA, right? Because we want to use Cauchy-Schwarz. So AH minus HA, okay? And how can we see this? Well, if you think about it, let's just write what is in the middle here. What is in the middle here? We have, we can do HA times A dagger minus, and then here we can do, let's say, let me just write, because it's the trace of A, sorry, let me write the other way, write the better way. So we have AH minus HA. So then here, the trace is like, let's say AH minus HA times a dagger, right? So we would have here like HA times a dagger, and then we have minus, and then here we're gonna have exactly by the cyclicity of the trace, I can take this A to like the front. So we have AH times a dagger, right? But the trace of this is exactly, so if I put the trace of this guy, this is exactly the inner product between, well, AH minus HA, inner product with A, because remember, this is the trace of the first matrix times the second matrix transpose, right? So then we have the square. Okay, so now we wrote it in this way, and you can see here that this guy is the inner product, right? So if we call like this matrix A like B and this one C, so we have that this is the inner product of B and C, and this is exactly like the norm of B squared, and this is the norm, this one is the norm of C squared. So therefore, we have that the Hessian that we just computed at A is greater or equal to 0. So we get the G convexity, right? And now, how do we prove? So we have geodesic convexity, and now all we need to prove is smoothness, right, of our matrix. So how do we prove the smoothness of our function f, right? So from the Hessian, what do we know, right? So now we computed the Hessian, right? So from the Hessian, okay, so from Hessian, we know that for all Hermitian matrices H, right, like which are the derivatives, we have that the inner product, when I take H and I take del squared FAH, we get what? We get exactly 1 over the norm of A to the 4th times the inner product of A squared times the inner product of AH minus HA squared minus the inner product of A and AH minus HA. Correct? And now, and this is squared, sorry. And then we can think about this as, oh, if we take the absolute value, right? So if we take the absolute value, so this is less than or equal to 1 over, like, so I put here, like absolute value. We have that this is less than or equal to 1 over A to the 4th. Well, we know this is always non-negative, right? So this is, and then we can do what? We can do this guy plus the absolute value of the other one. So we have A squared times AH minus HA squared plus the absolute value of this AH minus HA squared. But this inner product, as we saw, if we just use Cauchy-Schwarz, this is less than or equal than the absolute value of A squared times AH minus HA squared, which means that this ends up being like less than or equal than 2 times the norm of H to the 4th times norm of A squared times the absolute value of AH minus HA squared. But now, if you think about this, if we just use the triangle inequality here, we just do, so if you use triangle inequality, this is less than or equal, then the norm of AH plus the norm of HA and all of it squared, right? Just by the triangle inequality. Triangle inequality. And then now, well, this guy here is equal to, well, 2 times the norm of A times the norm of H, right? And all of this squared. So in particular, what we get is in the end that this whole quantity here is less than or equal, and the 2 squared is 4, so we have like 8 norm of A to the 4th. Well, the norm of A to the 4th cancel with the norm of A squared, so we have like norm of A squared here times, and then here we have again norm of A squared times norm of H squared. But these cancel, so we get less than or equal to 8 times norm of H squared. And in particular, what does this prove, right? So we prove actually that, so in particular, we have that, so okay, so we prove just that H, the Hessian FAH is less than or equal than H times the norm of H squared, but this is exactly H times, well, H, and then I have the identity here, H, right? And this is for all Hermitian matrices H. So in particular, this implies that the Hessian of our function is less than or equal H times the identity. So it implies that we are 8 smooth. So now we prove that our function is convex, and we prove that the function is 8 smooth, so we can run the gradient descent algorithm and we get the convergence that we would like, right? And now, okay, now that we did this, now let's analyze what is the gradient descent doing. So if you remember from our formula for the gradient, our gradient is exactly what? So our gradient is the gradient of f at a is exactly 1 over the absolute value of a squared times a dagger minus a dagger a. Right? So now if our gradient goes to 0, so if like the norm of gradient of f of a is going to 0, right? Then if we say that, let's say, so, and let m, right, be equal to a over the norm of a. So in particular, we have that the gradient, like the gradient at a is just m dagger minus m dagger m, right? And in particular, what is this saying? Well, this is saying that the only way that the gradient can go to 0 is if, well, is if exactly like m dagger minus m dagger m is actually equal to 0, right? Or tends to 0. But if m prime, which is the equivalent to saying that m dagger is actually converging to like m dagger m, right? Like they're getting equal, they're getting like, they're becoming equal. Now, what does it mean for this inequality to happen? We know that this inequality happens if and only if M is a normal matrix, right? So in particular, our gradient descent is converging. So here, look at what the amazing thing is doing. So the gradient, this gradient descent will converge if it converges, right? Like if it converges to a normal matrix. But if it converges to a normal matrix, what do we know, right? So by the spectral theorem, right? What do we have? Well, by the spectral theorem, it is converging to a diagonalizable matrix. Right? So in particular, whenever our point converges to, like if your gradient converges to 0, then you know that actually you're taking your matrix and you're sending this matrix to another matrix in the orbit or in the orbit closure, which is diagonalizable, right? So in particular, we know that any non-nilpotent matrix in this case, right, like our gradient descent will actually make it converge to a diagonalizable matrix, okay? This is quite impressive that the gradient actually has a meaning in these actions as well. Okay, so this concludes our third lecture. And what did we learn today? So today we learned about the scaling algorithms for non-commutative group actions. We learned about geodesic convexity, and we're also able to generalize the gradient descent algorithm for geodesically convex problems. And then we actually solved the gradient descent for, like, rigorously solved for the conjugation action, and we saw the meaning of it, right? So in the next lecture, we're going to see actually a full analysis of a non-commutative scaling problem for the tensor scaling, and we're going to see like strong convexity, how strong convexity can be used to give us much better convergence bounds, just in the same way that it happens in the convex situation. And in the final lecture, we're going to see this application of these non-commutative scaling problems to statistics. Okay. All right.